Good morning. I want to start section 2 of chapter 13 today, and I'm going to do it by example of what's in the textbook. Example 13:4 discusses cocaine addiction. It says chronic users of cocaine need the drug to feel pleasure. Perhaps giving them a medication that fights depression will help them stay off cocaine. A 3-year study compared the antidepressant called desipramine with lithium, which is a standard treatment for cocaine addiction, and a placebo. The subjects were 72 chronic users of cocaine who wanted to break their drug habit. 24 of the subjects were randomly assigned to each treatment. Here are the counts and the proportions of the subjects who avoided relapse into cocaine during the study. We had 3 groups, 1, 2, and 3. We had the group that had desipramine, lithium, and the placebo. There were 24 subjects in each group, and if we just look at the ones who did not relapse, there are your numbers. Now it's easy to see from those numbers that desipramine had a better no relapse rate than lithium or placebo. In fact, if you look at the proportions, 58.3% of the desipramine group was able to stay off cocaine, while just a quarter of the lithium group and 17% of the group who received the placebo. If we had analyzed this question back in chapter 12 with proportions, we'd have to compare P1 to P2, P1 to P3, and P2 to P3. It'd take a while. I don't think it would be difficult, but it would take us a while. The good thing is, now in chapter 13, we can use a chi-squared test to analyze all 3 of them at once. In fact, this type of test is called a chi-squared test for homogeneity. Now you look at that word and you think, I have no idea what that means, but you probably do. Homogeneity just means, is this group the same throughout? In other words, if I divide these people up into these 3 groups, are they the same really, whether they're in the desipramine group, the lithium group, or the placebo? The test looks a little different. We use a matrix instead of a list, but the formula, the idea is very similar to the chi-squared goodness of fit test that we've talked about the last few days. First, let's write the HO and HA. HO for this problem is the proportions of, I guess, non-relapse are the same regardless of treatment, and your HA is not that. The proportion of non-relapse is not the same regardless of treatment. The next thing we want to do is come up with a table called an RC table, and RC stands for row and column. For this problem, we're actually going to have a 3x2 table. We've got the desipramine group, the lithium group, and the placebo, and we've got the patients who did not relapse and the patients who did relapse. Now we know from earlier that there were 24 people in each group for a total of 72 people. They also gave us the numbers of non-relapse, which were 14, 6, and 4. Simple subtraction will tell us that the other column, the relapse numbers, need to be 10, 18, and 20, and then I can total up those columns to get the totals of the columns. Notice that the blue numbers weren't included when we called this a 3x2 table. The red numbers I have here are the observed values. The next thing I need to come up with is the expected value for each cell. Well, If I look here, 24 out of 72 of the patients did not relapse. 24 out of 72. If my HO is true, that 24 out of 72 should be without concern for whether disipramine the biggest, lithium's the biggest, or the placebo is the biggest. I know that there were 24 people in each group. This proportion of non-relapse, which reduces to a third, should tell me that a third of the 24 people in the disipramine group wouldn't relapse if in fact HO was true. So this would be 8. 24 over 72, or 1/3 of 24. Likewise, these numbers would be 24. And notice those still sum up to give me, of course, 24 people who didn't relapse. Again, I can use simple subtraction to come up with these orange numbers. And again, in the 3x2 table, I've got the expected values. Some of you like formulas. The formula for the expected value is column total times row total over table total. So the column total for the first column is 24. The row total for the first row is 24. And the table total is 72. So if you say 24 times 24 divided by 72, you should end up with the expected value. And you can go through the rest of this to see it's row total times column total over table total. I'm going to rewrite these observed and expected values here on another page. Oh, I bet I could. Can I do this? Yes, I can. Oh, that didn't work quite so well. All right, let's ditch this idea. I'll come back and rewrite them. So I gave you a little break. All right, here's my observed values. These are observed. My expecteds were 8, 8, 8, 16, 16, and 16. And that may not always work out where one column's all the same, but it did in this case. And then we're going to go through and use our formula just like we did with the chi-squared goodness of fit test. Some of you may be asking about conditions. I'll come back to conditions at the end of all this and explain how those fit in. But observed minus expected squared over expected. And I'm going to do that for each cell. I need a little bit more room on this one, so I'm going to draw it a little bigger. So the first cell, the top left cell, is observed minus expected squared over expected. Observed minus expected squared over expected. Observed minus expected squared over expected. You might not necessarily have to write this down for every single cell, but that's the idea of what's going on. So now in the first cell, it's 14 minus 8, that's 6. 6 squared is 36. Divided by 8, this cell worked out to be 4.5. 6 minus 8 squared, that's negative 2. Squared is 4. Divided by 8, it's 0.5. 4 minus 8 is 4 squared 16 divided by 8. That cell works out to be 2. And you're going to do that for each cell. These other ones, turns out to be 2.25, 0.25, and 1. Then, as the formula says, I add up all those numbers to get my chi-squared test statistic of 10.5. The graph, still right skewed, same curve. Here's 10.5, and this area is going to be my p-value. Now the trick here is to figure out what the degrees of freedom are. Let me go to a new page and we'll talk about degrees of freedom. Degrees of freedom, as we've stated for a long time, is the number of things you have to know before you can know everything. And actually, it's the fewest number of things that you need to know in order to know everything. Now, I was given this information. So if I start telling you information, what's the littlest I can tell you where you can still figure out what the answer is? Well, if I tell you this is 14, you can, of course, figure out that this one must be 8. Then if I tell you that this one is 6, you can figure out that this one is 18, but you can also figure out in the column that this must be 4, and then this number then must be 20. So for this problem, the degrees of freedom are 2. The formula, maybe we can discover the formula. If I had one like this, if I told you this one, wouldn't get you anywhere. If I added this one, you could then figure out this. Because again, remember, you were given these totals over here. We know what they add up to. Now if I throw this one in, you'll be able to figure this out. And when I throw this one in, you'll be able to figure this one out, and finally this one out. So for this problem, the degrees of freedom are 4. You might be able to see the formula for degrees of freedom are row minus 1 times column minus 1. Degrees of freedom are row minus 1 times column minus 1. So now I can go back to this. On my graph, I know it's a chi-squared test statistic with 2 degrees of freedom. Look on your blue chart or your chi-squared chart for 2 degrees of freedom and go over until you see 10.5. You'll get, in this case, a p-value somewhere between 0.005 and 0.01. So my p-value is between 0.01 0.005. Finally, write your conclusion. With such a small p-value, I have enough evidence to reject HO in favor of HA. I decide that the proportions of non-relapse are not the same regardless of treatment. Then you go back like we did before and you look in this table and you ask yourself, which one contributed the most to the chi-squared test statistic? Clearly it's here. So this cell is where the biggest difference was. This cell tells me that I observed way more patients on lithium who did not relapse, on dicipramine, who did not relapse than I thought I would. There were way more people who were taking dicipramine who did not relapse than I expected to see. That's where the biggest difference occurred. So we reject HO, then do the follow-up analysis. One other thing, of course, I needed to do was discuss the conditions required to even perform this test. And they're just like they were in the first section, the goodness of fit test. First of all, the one that we always like, the numbers or the subjects need to be SRSs from whatever group I'm looking at. So in this case, I hope that these cocaine addicts are like an SRS for all cocaine addicts. Of course, one thing we said was that these cocaine addicts were actually trying to quit, which is a relevant condition here. If we have two two populations, then our SRSs need to be independent SRSs. Next, none of the expected values can be 0, and no more than 20% of them can be less than 5. If they are, then you need to take a larger sample size. And you see here the smallest expected value was 8, which is clearly not 0 nor less than 5. So we're in good shape with that. Next thing I want to do is show you how to do all this on your calculator. Of course, you'll need to be able to write this down. You'll need to know this formula. You'll be required to know the formula for degrees of freedom. Same idea with conditions and writing conclusions and hypotheses and all that. But let's look at how to do it in your calculator. And this should work whether you have the TI-84 School Edition or not. Open your calculator. Open your calculator. Turn on your calculator. I've got to open mine. Stat test, chi-squared test. Might not be letter C, but chi-squared test is what you're looking for. And you notice that it gives you matrices. You'll be all right. I can do it, and I'm not real good on matrices either. So what I want to do is put these numbers into the matrix. It asks you for the observed and the expected. Now, we figured out the expected matrix by doing some calculations. Calculators are quite good at doing calculations. This matrix is not where it's going to find the expected values. It's where it's going to store the expected values. All you have to do is enter the observed values in matrix A. So go matrix, which was second inverse. There's matrix. And then I'm going to edit matrix A. Hit enter. And I want to make a 3 by 2 matrix. Type in your numbers. Then quit. Go back to your test. So I have now stored this observed value in matrix A. Matrix B again is where it's going to put these values. Now hit calculate. It gave me my chi-squared test statistic, my degrees of freedom, and we can tell that the p-value it told me is in this interval. This is just the more accurate one. Same thing I would get if I did chi-squared CDF, lower bound, upper bound, degrees of freedom. That's the same number it showed me up there. If I go back and look at matrix B, so go to matrix B, it gives me the 8 and 16. Now, one drawback of this function on the calculator is it doesn't give you these components or these contributing factors to the chi-squared test statistic, but it does give you the observed values and the rest of the details. So you'll have to, if you decide that you need to reject HO, you'll have to do this stuff, unfortunately, the long way. Or you can use computer software, and I've been remiss at discussing computer software for the last couple chapters, but let's look at what it would be like. This is the Minitab output for this problem, and computer output does not need to be a concern to you, but you do need to be familiar with it. So let's see if we can discover what all these different parts are. You notice here that it lists columns and rows, and they put the expected values and the observed values right on top of each other. So there's the observed, the expected, the observed, the expected. The observed values will always be integers because they're counts. The expected values, because it was obtained with a formula, might end up being a decimal. And they've got the totals for the rows and columns. These numbers, you might notice, are these numbers. And they put them where they go. So they're arranged like they were in the table. They give you the sum. Here's the degrees of freedom. That 2 is this 2. It's the chi-squared distribution with 2 degrees of freedom. That's my test statistic. But that's not my p-value. What is it? Well, for some reason, the developers of Minitab have decided to always report the area to the left of this. To be consistent, they did it with chi-squared, normal, t. That's the way they do it. So what we would need to do perhaps is look at this and decide if that number makes sense. If you're not sure, use this test statistic with this degrees of freedom on your chart or your calculator. Our p-value is actually 1 minus this because on the chi-square distribution we use the area to the right. Familiarize yourself with this kind of printout. So that pretty much wraps up the chi-squared test for homogeneity. Your homework over this for Friday is 17 and 21, but that should give you a good idea of how to work the problems. I'll also put this on the website.